Hello everyone. In this particular lecture, we are going to see about a reflection concept, reflection of electromagnetic waves. Okay. So, what are the reasons for getting reflection of electromagnetic waves? When the electromagnetic wave is traveling from one medium to another medium, it is possible. So, this is medium 1 and this is medium 2. These two are different media. Because these two are different media, these two media are having different relative permittivity, different relative permeability, so that these two are having different impedances. Okay, so because the impedance of these two media are different, what will happen means, when the wave is traveling from medium 1 to medium 2, surely certain portion of the signal will be reflected back. So what is the reason for the reflection? Impedance discontinuity. Okay, impedance discontinuity. We can say that is impedance mismatching also. Impedance mismatching also, or impedance irregularity also. So because of the impedance discontinuity, when the wave is traveling from one medium to another medium, then what is happening? Certain portion of the signal will be transmitted to the other medium, but certain portion of the signal will be reflected back. Okay, and this analysis can be done in two ways, based upon the angle of incidence also. That is what we are going to see in the next slides. So here very important thing is, what is the reason for the reflection means, first of all you need to understand that there is a difference in the impedances. Because of that reason, the electromagnetic wave can be reflected back. Next, types of the reflections possible. So reflections possible means, here this is based upon the angle of incidence. Actually this is based upon the angle of incidence. So as I said, here this is an interface. This interface is separating two media, here medium 1 and here medium 2. These two media are separated by this interface boundary. We are seeing here line, but actually two media can be separated by a sheet, plane or surface. So we are seeing the view of this particular interface in this way. So you are observing a line, but actually what is that one? Sheet. Okay, this sheet is separating the two media. Okay, then so it is a plane. So which plane we can consider in our analysis means, so you can take any plane, and in my lecture I am taking this is XY plane. Okay, that means x-axis is here and y-axis is coming towards you. So dot circle I am using for the axis, for the vector which is coming out of the screen. So dot circle. If you use cross circle, what is the meaning that one? That particular vector or that particular axis is going into the board. Okay, so x-axis is changing like this, y-axis is changing like this. So this plane is nothing but the interface. This plane is separating the media, which is left to this one is medium 1 and right to that one is medium 2. In this manner, we are separating the media using this particular interface. So wave is traveling in this direction, or what is the another vector we can able to draw, another axis we can able to draw perpendicular to this plane is nothing but Z only, no? Z. Okay, if you extend this Z1, this one we can able to take as a normal to the interface. So here in this particular topic, you need to remember one thing, whatever the angles we are going to see, angle of incidence, angle of reflection, angle of transmission, all these things are given with respect to this interface normal only. Okay, not with respect to interface. okay, with respect to normal of the interface. Okay, so this is the interface. So perpendicular to this one is the normal of the interface. So like this. So this is nothing but our z-axis only. So this z-axis itself we are considering as normal to the interface. Normal to the interface. Okay. So here this is the situation you can take in all the reflection possible cases. Okay. This is the situation you need to understand. So medium 1 may have the impedance eta 1 and medium 2 should have different impedance, that is eta 2. Because of this impedance mismatch only reflections are coming. Okay, so what we can do here, for example, this particular electromagnetic wave is incidented like this, okay, on the interface. So because already impedance mismatch is there, so that certain portion of this signal will be transmitted into the medium 2 and remaining portion will be getting reflected into medium 1 only. Reflection means the direction will be changed, na? So like this it will come. So in general, in this particular case, the incident wave is having the direction of z, the transmitted wave is having the direction of z, but the reflected wave is having the direction of minus z. Okay, so this is one thing. One case. What is this case means? Here what is the angle of incidence? This angle of incidence means this is an incident wave, na? So that angle of incidence is given with respect to this wave, and angle of reflection is given with respect to reflected wave. Angle of transmission is given with respect to this transmission wave. So theta I, theta R, theta T. Angle of incidence, angle of reflection, angle of transmission. These three are given with respect to normal to the interface, not with respect to interface, with respect to normal to the interface. That is what you need to remember. So this is the interface already I have given. This is a normal to the interface. So how much angle this incident wave is making with respect to this normal? These two are in parallel. So angle of incidence is equal to 0. Similarly, again the wave which is reflected back is making 0 degrees with the normal to the interface, so theta r is also 0. Similarly, the angle of transmission can be given as 0 only, because the transmitted wave is in parallel with this normal to the interface. So again theta t is equal to 0. So in this manner you can able to take the values of theta I, theta r, theta t, so that here what is happening here, what is the nature of this particular reflection means we can able to call this one as, okay, in this particular criteria we can able to take as normal incidence. This entire criteria can be taken as normal incidence. So why the name was given for this one? The incident wave has given normal to the interface, okay, has been sent, okay, the incident wave or the electromagnetic wave has been incident on the interface in such a way that is normal to the interface. That's why this is called normal incidence. This is one thing is possible. And here in this particular case, theta I is 0, theta r 0, theta t is equal to 0. There is another case, that is instead of sending the electromagnetic wave which is making the angle theta I is equal to 0, here non-zero theta I we have to take. That means what is happening, you see. So as I said earlier, this is medium 1 having the impedance is eta 1, this is medium 2 having the impedance is eta 2. So because of the impedance mismatching, what is happening? Reflections are possible. This is x direction and positive y direction is coming towards you. This is a normal to the interface, and this side also you can take normal to the interface like this. Okay, then what we need to say, if you send the electromagnetic wave like this case already we have seen, since the electromagnetic wave is incident normal to the interface, that is called normal incidence, that is over. But here what we are doing in the sense, instead of sending the electromagnetic wave in such a way that is making 0 degrees with the normal to the interface, what we need to do in the sense, we need to send the electromagnetic wave in such a way that we need to incident the electromagnetic wave in such a way that it is making certain amount of non-zero angle theta I, angle of incidence is now non-zero, certain amount of angle of incidence is there with not with the interface, with normal to the interface. Okay, with the normal to the interface it is making certain amount of angle, that is called angle of incidence theta I. So it is having certain amount of arbitrary angle, so that this particular case is called oblique incidence. Oblique incidence. So these are the two topics we have in case of the reflection. One is normal incidence, where electromagnetic wave is transmitted or the incident on the interface in such a way that it is making 0 degrees with the normal to the interface. But here non-zero angle is made by this incident wave with respect to normal to the interface. Certain amount of angle is there. So anyhow, because of the impedance mismatches, what will happen? Certain portion of this signal will be reflected back into the same medium, and that is also making certain amount of angle with the normal to the interface. So that is called angle of reflection, and remaining portion of the signal will be transmitted into the another medium, and this is also making certain amount of angle with the normal to the interface, that is called theta t. So here also we have angle of incidence theta I, angle of reflection theta r, and angle of transmission theta t. So in this manner we have these three angles. Okay, and here using Snell's law we can able to have the relation among these three, and using the first one we can write theta r is equal to theta I. That means angle of reflection is always equal to angle of incidence. Then sin theta t by sin theta I is equal to root of mu1 epsilon 1 by mu2 epsilon 2. So this is giving the relation between theta t and theta I. This is giving the relation between theta r and theta t. Okay, sorry, theta r and theta I. So in this manner we can able to have some knowledge, some introductory knowledge on normal incidence and oblique incidence. Okay. Now normal incidence. Already I have mentioned that one. So this is the interface you have to consider. So in our analysis we have taken XY plane is the interface. So y-axis is coming towards you, positive y-axis. This is the x-axis. So this is nothing but our interface. So for this interface, normal is nothing but this red color line is representing, okay, normal to the interface. So that is in the direction of Z. So you can extend that one. So this is also normal only. So this is the incident wave, incident on the interface, and this is exactly parallel with the normal. So here theta I is equal to 0. And because of the impedance mismatching eta 1, eta 2 in between these two media, so what will happen? Certain portion of this signal will be reflected back. This is called reflected wave, and which is making the angle 0 with respect to normal to the interface. And this angle of transmission also is equal to 0, and this is a transmitted electromagnetic wave. This is in parallel with the normal to the interface only. So that theta t is equal to 0. So this is what already we have seen. Okay. Then oblique incidence. Already this concept I have told. So this is a normal, this is an incident wave which is making the angle theta I, reflected wave is making the angle theta r, and the transmitted angle is making angle theta t with the normal to the interface. You should not take like this. If you take like this, what is the meaning? It is making the angle with the interface, but this is the angle made by the transmitted wave with the normal to the interface. This is normal to the interface. Okay, Snell's law already I have given. Okay, these two angles are same, and the relation between theta t and theta I is given by sin theta t by sin theta I formula. Okay. Then normal incidence analysis we will see now. Okay. Now concentrate very carefully. So as I said, we are extending that particular topic now, normal incidence. So this is x, this is y, and this is z. This is common, already we have discussed about this one. Now we are telling that electromagnetic wave has been incident in this manner. Electromagnetic wave has been incident in this manner. Okay, and because of the impedance mismatches, eta 1, eta 2, certain portion of the signal will be reflected back, remaining signal is transmitted into the another medium. Okay. So here what we will do in the sense right hand thumb rule, the application of the right hand thumb rule is very very important. So before applying that right hand thumb rule on this particular structure, here only I will show to you before application of that one. So you need to understand that one very carefully. So according to pointing theorem, we know that this electric field is in cross product with H bar, okay, will give the pointing power vector. Like this we can able to take. This is the power density actually. So the instantaneous power density P bar is equal to cross product of electric field intensity and magnetic field intensity. So the direction of E bar, that is in cross product with the direction of H bar, will give the direction of the P bar also. Like that we will take. Okay. So for that, right hand thumb rule will be very much helpful. So how to do that one means, thumb is representing the P bar. Thumb is representing the P bar. That means wave direction or the power flow direction. So in our case, we are working with respect to wave direction. So you can consider right hand thumb is representing. You need to keep your 3 fingers of your right hand like this. Okay, forefinger, middle finger, and this particular this thumb also you should keep in such a way that perpendicular to each other. Okay, then this thumb is representing the direction of the wave, this forefinger direction is representing the direction of the electric field, and this middle finger is representing the direction of the magnetic field. Okay, so right hand only we have to use. So in this manner you can able to utilize the analysis for this particular structure. Now see carefully, already we are telling that this electric field is the electromagnetic wave is moving towards this normal direction, that means in the Z direction. That means our right hand thumb we have to keep like this only towards the Z direction, like this we have to keep. So this forefinger is representing the electric field and this middle finger is representing the magnetic field. This is the analysis I have told. So you see here, already clearly I have told that dot circle is nothing but coming outside. Okay, and cross circle is nothing but inside. The vector or the axis should go inside when you use the cross circle, and when you use the dot circle, the vector or the axis should come out of the screen. Like that you have to take care. So as I said, this is a wave direction. So we have to keep in the direction this particular electric field. This particular thumb of the right hand, then this forefinger is upside, which is representing the electric field, and this particular middle finger is representing the magnetic field. That's why here dot circle we have taken. So this is the direction of the wave. That one we can able to take as the K bar. Direction of the wave is nothing but K bar we can able to represent. Next this one is electric field already I have told, and what is coming out of the screen? Magnetic field. So in this manner you can take, and these are incident wave only so you can able to take EI, HI, KI, like this you can able to take. Okay, now coming to this reflected wave. So in this manner wave is transmitted and incident on the interface, and because of the impedance mismatch it is reflected back. So you see how did I change my fingers of the right hand. So in this manner we have incident and suddenly it is reflected back like this. Whenever it is reflected back, you need to see very carefully that the direction of the propagation is changed. Okay, whenever we are incidenting, direction of propagation is towards the positive Z direction. But whenever it is reflected, the direction should be given in such a way that is in the negative Z direction. Okay, so this is the incident wave going and incidenting on the interface, and because of the impedance mismatch, it is reversed like this. Whenever it is reversed, this thumb is representing in the negative Z direction. That means it is reflected wave, but this particular forefinger is again representing upside only, towards positive X direction only. That means there is no change in the electric field vector. So reflected wave electric field is also towards positive X direction only. But here, what is this one? Negative Z direction is available for the KR. That means reflected wave. What about magnetic field? You see here magnetic field is given by this particular middle finger. It is coming out of the screen for the incident wave, but whenever it is reflected, it is going into the screen. Is nothing but a cross circle. That's why here we have represented with the cross circle. So this is represented by this HR. Okay, so incident is over and reflected is over. Transmitted is very simple, because whatever the positions we have taken for the incident wave, same thing will be there for the transmitted also. So that we can take here ET, this is HT coming out of the screen, and this is KT. This is representing just propagation. So in this manner we have taken the representations of the normal incidence of the electromagnetic wave for this particular interface. Okay, so here main thing is the electric field of this incident wave and reflected wave and transmitted wave, three are in the same direction only, but the magnetic field representation of the incident wave and reflected wave are in reverse direction. Okay, while it is transmitting, while it is incidenting, it is in the positive y direction. Okay, it is coming out of the screen, that means positive y direction, but whenever it is reflecting back, then it is going into the board, that means a negative y direction. So there is a change in the incident magnetic field and reflected magnetic field. Okay, so in this manner you need to understand very carefully regarding this particular normal incidence. Applying the tangential components relation. Okay, so anyhow in medium 1, this entire thing is medium 1 only, na? Medium 1, and this side we have medium 2. Medium 2. So in medium 1 we have two electric fields and two magnetic fields. Okay, this is one magnetic field, this is another magnetic field. So what is the tangential component here is nothing but two electric fields we have to consider into the account, and two magnetic fields also we should consider into the account. And this side only one wave is there, so only one tangential component of the electric field, only one tangential component of the magnetic field. Okay, magnetic field is nothing but this one, this is the propagation. Okay, so like this we have to take. So for example, according to this boundary conditions, we know that tangential components of medium 1 is equal to tangential components in medium 2 for the electric field. Okay, so ET1 is equal to ET2, that is the condition we can see in the boundary conditions of the electrostatics we have considered. So now if you observe, ET1 means here in medium 1 we have two things. One is incident tangential component, okay, plus reflected tangential component. It is equal to transmitted tangential component. This is in medium 2. Okay, instead of having all these suffixes, simply I will take EI plus ER is equal to ET. Simply I am taking like this. Okay, then this is one of the equations we have. Now what we need to write for the magnetic fields? Anyhow, we are assuming that this particular boundary is current free. Okay, this particular boundary is current free. So that what are the equations we'll get? Generally E by H is equal to eta, na? So H is equal to what we can write? E by eta. So EI by eta, because there is a change in the direction for the magnetic field of the reflected wave, minus I am taking, then ER by eta, it is equal to ET by eta. But it is eta 1 here, because these two are available in medium 1 only. That's why related intrinsic impedance is equal to eta 1. And for transmitted wave is available in the medium 2. That's why here eta 2. Then you replace this ET with this particular equation. Then you can able to get the formula for ER by EI just by rearranging the equations. So simply you will get ER by EI, that is equal to eta 2 minus eta 1 by eta 2 plus eta 1. So this is called reflection coefficient, and here we are representing that one with tau. So tau is the reflection coefficient. This is the ratio of this reflected electric field to the incident electric field. And in terms of the impedances, if you see, that is eta 2 minus eta 1 by eta 2 plus eta 1. Actually what I told in the beginning, the reflections are due to because of the change in the impedances. Okay, because of the change in the impedances. If you see the reflection coefficient formula, here the difference between the impedances is available. For example, here impedance is given by 50. Okay, eta 1 is given by 50. And here eta 2 is given by 100. Eta 2 is given by 100. Find the tau, that means reflection coefficient means easily we can able to calculate by using this particular formula. So how much we'll get? Tau is equal to, we'll get 100 minus 50 by 100 plus 50. 100 plus 50. So that is equal to 50 by 150, that is equal to 1 by 3. Like this we'll get. Tau is equal to 1 by 3 we'll get. For example, here I have taken eta 1 is equal to 50. If this eta 2 is also 50. Eta 2 is also 50. Now you calculate tau. 50 minus 50 means you will get 0. You will get 0. That means reflection coefficient is 0. Reflection coefficient is 0 is nothing but ER by EA is equal to 0. If you cross multiply, ER is equal to 0. ER is equal to 0 means the reflection wave is 0. That means reflections are 0. Okay, reflections are 0. This concept is very important. Here reflections we are getting 0 when you take here same amount of impedance in the two media. When it is possible, two different media are having the same amount of impedance means what is the meaning of that one? Those two media are same media. Those two media are same media. That means in the same medium, okay, you will not get reflections. When there is another medium with a different impedance, then only reflections will be possible. Okay, this formula is very important. So reflection coefficient tau is equal to, from the definition we can take, it is the ratio of the reflected electric field to the incident electric field, and the formula in terms of the impedances is given by eta 2 minus eta 1 by eta 2 plus eta 1. Okay, and from this we have taken some conclusions that when you have the difference in the impedances, then only you will be having the reflection coefficient. That means then only you will be having the reflections. Okay, when you have no change, there is no reflection. There is no reflection. Next, what is the range of this particular reflection coefficient? Tau is nothing but, you see here very carefully, this numerator is always lesser than the denominator. Na? This numerator is always lesser than the denominator. That means it is always less than 1. It is always less than 1. If there is no reflection, okay, if there is no reflection, then what is the value of tau? 0. Okay, so minimum value is 0. For example, if everything is reflected back, whatever you have transmitted, whatever you have incident, everything is reflected back. That means these two are same. Okay, whatever you have incident on the interface, everything is reflected back means in magnitude, these two are same. That means the ratio is equal to 1 you will get, because ER is equal to EA. That means maximum is 1. Minimum is 0 when you don't have the reflection. Maximum is 1 when everything is reflected, so that this particular reflection coefficient magnitude is given in between 0 and 1. Like this we can take. Okay, so this is about reflection. Similarly, you can take the another concept called transmission. Okay, so that we can see in the next slide. So reflection coefficient, just now I have explained in the previous slide only. So here I am writing the formula eta 2 minus eta 1 by eta 2 plus eta 1, and the basic definition is it is the ratio of reflected electric field and the incident electric field. Okay, what is the range of this one? 0 less than or equal to mod tau is less than or equal to 1. Then transmission coefficient. So reflection coefficient is nothing but tau, that is equal to ER by EI. Okay, this is reflection coefficient. Similarly, here we can able to define about the transmission coefficient. So transmission coefficient generally represented with T, that is the ratio of the transmitted signal to the incident signal. Very simple thing. Okay, so in a similar steps, how we have done the derivation of this particular thing, you can do this one also very easily. So that finally you will get T is equal, that means transmission coefficient is equal to 2 times of eta 2 by eta 2 plus eta 1. And below of this one only I am writing the formula for tau also once again, that is eta 2 minus eta 1 by eta 2 plus eta 1. Can you write this T in terms of tau? Yes, it is possible. That is T is equal to 1 plus tau. Just you put here 1 and take the LCM. In the numerator also you will get eta 2 plus eta 1. So eta 1s will be cancelled. In the numerator you will be leaving with 2 times of eta 2, and in the denominator you will be leaving with eta 2 plus eta 1. Okay, so this is the relation between the transmission coefficient T and reflection coefficient tau. That is T is equal to 1 plus tau. Okay, so in this manner we can able to define the transmission coefficient. Relation between reflection coefficient and transmission coefficient just now I have completed, that is T is equal to 1 plus tau. Then percentage of power reflected. Okay, so power reflection means, first of all, reflection means we have the idea about that one, that is tau. But they have told about power, so you have to square this one. So percentage of power, that means you need to multiply with 100. Okay, then Here something they have given. Eta 1 minus eta 2 means what will be the value of tau? Already I discussed about this one. So tau is equal to eta 2 minus eta 1 by eta 2 plus eta 1. So when you have the same values, that means you are in the same medium. Okay. So what is happening here? Eta 2 minus eta 1 is equal to 0 because these two are equal. So tau is equal to 0 you will get. And when you have eta 2 is equal to 0, when you have eta 2 is equal to 0, what is happening here? Carefully you observe. This is the formula for tau now. Now you take tau, eta 2 is equal to 0. So this portion is 0. That means minus eta 1 by eta 1. So eta 1 will be cancelled. You will get minus 1. Tau is equal to minus 1. Tau is equal to minus 1 means now what is the basic definition of tau? ER by EI. So if you cross multiply this one, so ER is equal to, you will get minus EI. So what is the meaning of this one? What is the meaning of this one? In magnitude these two are same, but here a minus symbol is there. What is the meaning of that one? The reflected wave is 180 degrees out of phase with the incident wave. Okay, so in magnitude this is 1, that means completely reflected. When you don't have eta 2 value, that means when eta 2 value is equal to 0, what is happening means the total incident wave is reflected back. It is reflected, that is okay, and while reflecting it is making 180 degrees angle with the incident wave. Okay, that is what we have to observe here. But okay, this everything is okay. Why do we take here eta 2 is equal to 0? Okay, what is the necessity of that one? It is not a fun thing to substitute simply eta 2 is equal to 0. There is a meaning for this one. Impedance is equal to 0 means it is a purely conductor. So when you have medium 2 is the conductor. When you have medium 2 is equal to conductor, what is happening here? Everything is reflected back. So this is the criteria here. You take, this is the medium 2, and this is our interface. Okay, this is our interface, and which is separating the medium 1 and medium 2. And specifically what I have taken, it is eta 1, it is eta 2. Here I have taken eta 2 is equal to 0. Why? Here sigma is equal to infinity. That means conductivity is equal to infinity. Conductivity is infinity means what? It is purely conductor. Perfect conductor we have taken. So when the electromagnetic wave is traveling and incident on the interface, and this side what is there? Perfect conductor is available. So when you have the perfect conductor, its conductivity is infinity, so that this particular impedance is equal to 0. Impedance is equal to 0. When you have impedance is equal to 0, then what is happening here according to this reflection coefficient formula, eta 2 is equal to 0 means everything is reflected back. We have got here tau is equal to minus 1. That means everything is reflected back. That means in the conductor there is no chance for the propagation of the electromagnetic wave. Okay, that is the meaning of taking this eta 2 is equal to 0. So we have given one important conclusion that electromagnetic wave propagation is not possible in the conductor. That is what we have to take care. Okay, that is the thing. Then now we are entering into oblique incidence. Okay, normal incidence is over. Now we are entering into oblique incidence. So in this case again we have two types. One is parallel polarization, second one is perpendicular polarization. Generally polarization means we know about electric field polarization. So here also based upon the orientation of the electric field only, this particular oblique incidence criteria have been defined. Okay, based upon the orientation of the electric field with the angle of incidence or the plane of incidence only, we have taken here two types again. One is parallel polarization and second one is the perpendicular polarization. Okay, so that is what we are going to see. But first of all, what is oblique incidence means already in the basics I have told. This is x-axis, this is y-axis coming out of the screen. Same thing we are following. Okay, same structure we are following. So interface is the xy plane. Interface is the xy plane. Normal to the interface is the z-axis. So this is the z only. So normal is z and this is xy plane is the interface. Okay, or the boundary. So previously our electromagnetic wave is incident in this manner. That means it is making theta is equal to 0 with the normal to the interface. But in case of the oblique incidence, the electromagnetic wave should make certain non-zero angle with the normal to the interface, not with the interface. Okay, with the normal to the interface, it should make certain amount of angle, that is theta I. Then The reflected wave can also make certain amount of angle with the normal to the interface represented with theta r, and this is reflected wave. Okay, and because of the impedance matching, these reflections have been occurred, but total signal did not come. Certain amount of signal, there is a chance for the certain amount of signal to be transmitted also, that is this one, and this is making certain amount of angle with the normal to the interface, that is theta t. This is the situation I have told already. Now here we need to represent what is the orientation of the electric field and magnetic field for the three waves. For the incident wave we have to represent electric field and magnetic field, and for the reflected wave again we have to represent the directions of the electric and magnetic fields. For the transmission line also, for the transmitted electromagnetic wave also, we have to provide the directions of the electric field and magnetic field. So follow this one very carefully, it is somewhat confusing also, so listen carefully. Now parallel polarization we have taken. Okay, so parallel polarization. Okay, before going to see this parallel polarization, what we need to do, you see very carefully. So this is the interface na, x, and this is y, this is the normal to the interface, and this is also I am extending the normal. So as I said, we are sending this particular electromagnetic wave incident on the interface by making certain amount of angle theta I with the normal to the interface. Okay, so again right hand thumb rule we have to apply. Okay, so before going to see that one, we need to define one thing, that is plane of incidence. Plane of incidence. So because it is the this is the incident wave, we can represent with its corresponding vector is ki bar. Okay, and this is the reflected wave, the corresponding vector is represented with kr bar. Transmitted wave corresponding vector is represented with kt bar. Okay, so plane of incident is nothing but this ki, this kr and kt and normal to the interface, that is an cap. These three are available in one plane. That plane is plane of incidence. Okay, that plane is plane of incidence. And if your electric field is available in parallel with this plane of incidence, that is called parallel polarization. If your electric field is perpendicular to the plane of incidence, that is called perpendicular polarization. Okay, for interview questions also it is important. What is parallel polarization? What is perpendicular polarization means? Again we are telling with respect to electric field only. If your electric field is parallel to the plane of incidence, what is this plane of incidence? In which plane ki, kr, kt and normal to the interface, all these things are available. That plane is called this particular, we can able to tell this particular plane of incidence. And in this particular situation, what is the plane of incidence? In this particular situation, what is the plane of incidence? You see carefully. Interface is xy plane, but ki, kr, kt and normal are available on the screen. What is the plane of this particular screen? xz plane. So xz plane we have to consider as the plane of incidence, because on that plane only ki, kr, kt and normal to the interface are available. And your electric field, if it is in parallel with this particular plane, then we can tell that is parallel polarization. If it is perpendicular, that is called perpendicular polarization. And here we are going to see parallel polarization. Okay, so this is the plane of incidence na? So you have to take electric field in such a way that, you see again right hand thumb rule. So simply I am keeping like this. This thumb is representing the direction of the propagation of the incident wave ki. Okay, like this. So electric field should be available within the plane of incidence. So electric field will be taken like this. Magnetic field is coming out of the screen. Okay, so electric field is represented like this, EI, incident electric field. So magnetic field is coming out of the screen, so that dot circle I am using. This is HI. This is very, very important. Okay. Next, we will talk about this particular reflected wave now. So wave is reflected in this particular direction. So our thumb should be representing in this direction only. Okay. So in this direction our thumb should be represented. Okay. Then our this particular electric field should be available in such a way that is parallel to this particular plane of incidence. Okay, electric field should be in such a way that is parallel to the plane of incidence. Like that only we have to take. Like that only we have to take. So if you keep your thumb in such a way that this is traveling in the reflected wave, then your magnetic field is again coming out of the screen only, and electric field is going this way. Okay, so like this you have to represent. Okay, so in this manner, if you can able to represent, here we have to draw that particular thing. Next, coming to again transmitted wave. Transmitted wave is simple because it is similar to this particular incident wave only. So that we can able to represent like this easily how we have represented this particular thing. Okay, so next, plane of incidence. Just now I have told the topic is completed. Next, now you can see this one. Okay, so it is about the parallel polarization. So medium 1, medium 2. So z is equal to 0 means xy plane. So y is coming out of the screen. This is z axis. This is medium 1. This is medium 2. Angle of incidence, angle of reflection. So as I said, it is the direction of propagation of the incident wave. Electric field, the magnetic field is coming out of the screen. Okay, so you can able to check like this. You can able to check like this. So this is representing electric field. This is representing the direction of propagation, and H field is coming out of the screen. Like this we have taken. Okay. Now reflected wave you observe. Reflected wave if you observe, so it is reflecting like this now. So very easily, this thumb is representing the reflection wave. This forefinger is representing the reflected electric field. Okay, and this middle finger is going into the screen. That's why cross circle. Okay, and as I said, this incident wave and transmitted wave will be represented in a similar manner because it is also like this only. Okay, this angle may be different. Okay, just it is like this or like this, so that the orientations will be given by the right hand thumb rule in a similar manner. Then, for that particular parallel polarization, we have, after doing the derivations, you will be having this particular reflection coefficient is like this, and the transmission coefficient is like this. And what is this Brewster angle? I will tell about that one. But instead of taking these formulas directly blindly like this, I will give certain criteria regarding this particular thing. Okay, here theta I, theta R, theta T are available. So, in case of normal incidence, what is theta I? 0. What is theta R? 0. And what is theta T? 0. Okay, if you substitute here cos 01, cos 01, cos 01, cos 01, so it will be reduced to eta 2 minus eta 1 by eta 2 plus eta 1. So this one already we have derived in case of the normal incidence. So in the normal incidence, the angle of incidence, okay, is 0. Why? The electromagnetic wave is not making any angle with the normal to the interface. Similarly, reflected wave, similarly transmitted wave. So all these angles are 0. So if you substitute, you will get the reflection coefficient formula in case of the normal incidence only. So you can verify like that. But here we have some non-zero values for the angle of incidence, angle of reflection and angle of transmission, and the resultant formula will be like this. So eta 2 cos theta t minus eta 1 cos theta I by eta 2 cos theta t plus eta 1 cos theta I. Similarly, you will get the transmission coefficient formula also. Again same thing, substitute theta is 0 and theta t is equal to 0, 1 by 1 is equal to 1, so that you will get t is equal to 1 plus tau. This is what we have observed in the normal incidence. Normal incidence. So we will see the this definition of this particular Brewster angle now. Okay, so you see here carefully, this is the normal to the interface, this is x and y is coming out of the screen. Wave is incident like this by making certain angle theta I. So because of the impedance mismatch, something is reflected and something is transmitted. Okay, so here we can have 0 reflections. Actually, to have the 0 reflections, what is the criteria? To have 0 reflections, what is the criteria? Eta 2 must be equal to eta 1. Then tau is equal to 0. Reflection coefficient is 0. That means reflected wave is equal to 0. But even you don't have this condition, even you don't have eta 2 is equal to eta 1, you can achieve, even you don't have this one, means eta 2 is not equal to eta 1 only, even though you can have reflected electric field or the reflected magnetic field is equal to 0. How it is possible means you need to adjust this theta I. Okay, you need to adjust this theta I in such a way that there is no reflection. That means entire incident signal will be transmitted into the another medium. So for what incident angle it is possible, that incident angle is said to be Brewster angle. Okay, very very important. So for what value of the angle of incidence, this entire signal will be transmitted, like that we can tell, or no reflections will be possible, or we can tell reflection coefficient is equal to 0, okay, or transmission coefficient is equal to 1. In any manner we can tell no reflections, or entire signal is transmitted, or this reflection coefficient is equal to 0, or transmission coefficient is equal to 1, like that anything we can able to tell. Point is same thing, okay, same criteria. So for what value of the angle of incidence it is possible, that angle is said to be Brewster angle. Okay, then now this is about the perpendicular polarization. Okay, this is about perpendicular polarization. So as I said, plane of incidence is nothing but what? This xy plane only. Okay, xz plane. Plane of incidence is nothing but xz plane. Now you observe here, EI bar is coming out of the screen perpendicular to the plane of incidence. Okay, and here also ER is perpendicular, ET is also perpendicular. That is nothing but what? Electric field is perpendicular to the plane of incidence. That means it is about perpendicular polarization. Okay, the directions you can able to achieve in a similar manner. So if you see here, direction of propagation is in the same direction, but electric field should come outside, like this. Okay, so this is representing the magnetic field, and this is representing the electric field, this is representing the direction of propagation. So in a similar manner you can able to understand these things. Okay, but every case, whether it is incident wave or reflected wave or the transmitted wave, electric field is coming outside only. And you know about this one, this is the direction of propagation of the incident wave, this is the direction of propagation of the reflected wave, this is the direction of propagation of the transmitted wave. Only one unknown is direction of this particular magnetic field intensity, that can be easily understood by the application of the right hand thumb rule. Same thing. Okay, already we know these two, so you need to keep the middle finger in such a way that it is represented in this manner. So easy to understand that one. Okay, here somewhat difficult to show, so you can able to practice that one. Okay, then corresponding to this particular perpendicular polarization, this is the equation for the reflection coefficient, and this is the equation for the transmission coefficient. So same formula we got now here in the normal incidence also, but here some change is there. So as I said, in order to get the equation for the this reflection coefficient for the normal incidence, what we need to take? Theta is 0, theta r 0, and theta t 0. Okay, anyhow here theta r is not there, so if you substitute zeros, cos 0 is 1, so eta 2 minus eta 1 by eta 2 plus eta 1 only you will get. And here also same Brewster angle definition will be available, what we have seen in the parallel polarization. Okay, so you need to adjust the theta I in such a way that there will not be any reflection. Okay, that particular angle is said to be Brewster angle. Now we will see the question related to this reflection. A plane wave E bar is equal to 10 sin of omega t minus 10x volts per meter in a lossless medium with mu is equal to, they have given 4 mu naught and epsilon is equal to epsilon naught, strikes another medium. Okay, so this is medium 1 with mu is equal to 4 mu naught and epsilon is equal to epsilon naught with another medium with a 90 degrees angle of incidence. Okay, 90 degrees angle of incidence is there, having mu is equal to 9 mu naught and epsilon is equal to epsilon naught. What is the reflection coefficient? So first you calculate the impedances related to this one. So impedance formula is square root of mu by epsilon, so it is equal to square root of 4 mu naught by mu naught. So this is equal to root 4 is 2, it is 120 pi na, root of mu naught by epsilon naught is nothing but, so how much you will get? 240 pi. And in medium 2, eta 2 is equal to root of mu by epsilon, this is equal to root of 9 mu naught by epsilon naught, so this is 3 into 120 pi. So this is 360 pi. You have two impedances. It is easy to calculate the reflection coefficient. So tau is equal to eta 2 minus eta 1 by eta 2 plus eta 1. So if you substitute the values, 360 minus 240, pi is anyway cancel, I am not writing. So 360 plus 240. So it is equal to, how much we will get here? It is 60 plus 60 means 120, it is 500, 600. That means 1 by 5, that is equal to 0.2. So 0.2 is available here. Okay. Now we will see the next question. An electromagnetic wave propagating in free space. So this itself is one media, is incident on the surface of the dielectric medium with parameters mu naught and 4 epsilon naught. So this is free space. Free space means directly we can write impedance is equal to 120 pi. Okay, and medium 2, it is a dielectric medium with characteristics mu naught and 4 epsilon naught. So what is eta 2? Root of mu by epsilon, that is equal to root of mu naught by 4 epsilon naught, that is equal to 1 by 2 into 120 pi, that is equal to 60 pi. Okay, so what we need to find, then what will be the magnitude of the electric field of the reflected wave. So first we will calculate the reflection coefficient. So tau is equal to, we have the formula, that is eta 2 minus eta 1 by eta 2 plus eta 1. So first one is 120 pi, it is 60 pi. So anyway pi's will be cancelled, I am not writing that one. So it is equal to 60 minus 120 by 60 plus 120. So it is equal to minus 60 by 180. This is equal to minus 1 by 3. What is this one? Reflection coefficient. That means it is equal to ER by EI. So what they are asking, the incident wave, the magnitude of the electric field of the incident wave is E naught. So incident wave means you can take here E naught. Okay, A is equal to E naught. What will be the magnitude of the electric field of the reflected wave? So you need ER. So it is equal to minus E naught by 3. Okay, so this is the option. Okay, thank you.